Hello everyone, so here's lesson 2 on our energy theme. Today we're going to learn about kinetic energy and something called the work energy theorem. Now, we have already established, I think in lesson 1, that when you do work, you are in the units. At the very least, you know that we're in the units of joules. And we could talk about that being a Newton multiplied by a meter, and then of course a Newton is kilogram meters per second squared times the meter. Well, that means that it's kilogram meters squared over seconds squared. And we've also done stuff in the past where we've looked at a system. Let's say it's a car and maybe it's traveling with a constant velocity this way. And we talk about forces acting. If suddenly the car applies its brakes, it's going to have a force acting against that motion, the force of friction. So one way would be to describe the system as the car. And then you can see that this force of friction is leaving the car. It's exiting the circle, it's exiting the system, and therefore I can say that work is being done to the car. And that's sort of where this idea comes from. Okay, so we can do work on a system which will change the energy in some way. So we have this statement that work is equal to a change in the energy. Now, this is the first time we come across the specific different types of energies, and these are really the ones that we classify as mechanical. So that would be kinetic energy, that's the energy to do with motion, gravitational potential, that is the energy associated with the gravitational field. Lots more on that to come in future topics. And as we'll see in this section of this series of lessons, we also have elastic potential energy. These are the three main types of mechanical energy. And we'll kick things off with an example coming from kinetic energy. I like to use the annotation capital E subscript K, because I do believe there is only one type of energy. There is only one energy, and we just describe the way that energy is transferred to different types. And so E is the important bit, E and then the subscript K. All right, we've seen this before. We can derive this in class if we like, but we'll just jump straight into it. We all know as a memorized formula that kinetic energy is half mv squared. Of course, joules. Now, we'll later in this course we'll also come across a different unit for energy, but for now this is going to be our standard, our fundamental unit. Not fundamental units, it's a derived unit, and we're going to be using the fundamental units of mass and v for speed. Now, notice that we're using speed, and that's because we don't really want there to be a direction. Energy is scalar, it doesn't have a direction. So that's something that's worth bearing in mind. Okay, let's get into an example, and hopefully things start to become a little bit more clear. All right, 45 kilometers an hour is an object, and it's got some kinetic energy as 120 kilojoules. So let's just convert right away. 45 kilometers per hour, we want to get rid of that and have it in meters and seconds. So let's go ahead and unit cancel out all the units. So kilometer cancels out there. That leaves me with 1,000 meters, and the hour is going to cancel there. So hours to seconds, 1 hour is 3,600. So that gives me a speed of 12.5 meters per second. Good. Also want to recognize that I've got 120 kilojoules. So that's going to be 120, and now kilo is times 10 to the 3. So it's 120 times 10 to the 3 joules. All right, first up, we've got to find its mass. So of course, we're going to use our kinetic energy equation, 1/2 mv squared. Now I know the energy, so tick, and I know the speed, tick. So I just have to rearrange this to solve for the mass. So I'm going to go 2 times EK divided by, oops, not the mass, divided by the velocity, or the speed, squared. And that's going to give me the mass. So plugging that in gives me a mass that is 1,536 kilograms. Now I just want to make sure I'm in the right sig figs. Looks like I need to use 3. We're going to ignore the dangling 0 for now, so let's just go 3. So 1.54. 1.54 times 10 to the 3 kilograms. That's my mass. Okay, so that's part A. Part B, it's saying that I now lose 70 kilojoules of kinetic energy, and we're asked to find the final speed, so that's assuming that the mass is going to stay the same. It's losing 70 kilojoules of energy. That means it's going to be 50 kilojoules, so 50 times 10 to the 3 joules. So I just took my 120 times 10 to the 3 minus 70 times 10 to the, times 10 to the 3, and that's going to give me 50. So the energy that I now have, the kinetic energy, is 50 times 10 to the 3, and I have to solve now for the speed. So let's write it all out. I've got my equation, solving for speed, so it's going to be 2ek divided by the mass, and then square rooted. That's going to give me the speed. Let's plug those numbers in, and I get a speed of 8.06, and I need to go to 2 sig figs, so that's going to be 8.1 meters per second. Okay, second example. We have an 8,000 Newton car. Now, remember, this is actually the FG, isn't it? This is the weight. The weight of the car is 8,000 newtons, and we know that FG is equal to mg, so, I don't know, maybe we're going to need the mass. So, 8,000 newtons divided by 9.81 meters per second squared is going to equal the mass. And that happens to be 815.49. Keep all those in there. That's kilograms. Okay, so we know the mass of the car. It is accelerating from rest. So it's going from a stationary position here, so VI of 0. It is now going to accelerate to a new speed of final velocity in this situation of 15 meters per second. So it's gone from stationary to some new position. We don't know the time, we don't know the distance, we just know there's been a change in the velocity. Okay. Now, we also are told that the propulsive force is doing work, and that work is 110 kilojoules. So, it's going to propel the car forward. Let's just have a little think about what this looks like. Here's my car. This is going to be the propulsional force. Let's call it the force applied. And there's obviously going to be some, let's do that from the middle. There's obviously going to be some friction. So the frictional force is going to oppose that, but obviously the net force is going to allow for this acceleration to the right. We could also, so now that we're talking about forces, remember we've got systems. We can say that, hey, this is a system, and the force applied is doing some positive work, and the force of friction is doing some negative work. But we do know that the work done here is going to be the work by the applied force minus the work from friction, right? Because we've got this way would be positive, this way would be negative in terms of these forces and the work done. And so that's my work net, and that's going to be equal to the delta EK. Okay, so let's keep going with that. I'll just move that out the way. Let's start filling this in. Well, the work done by the propulsive force is 110, so let's put that in. So 110 times 10 to the 3 joules minus the work done by friction, and that's going to equal the delta EK. Well, delta EK is going to be the final kinetic energy minus the initial, so let's put that in. So the EK final minus the EK initial, that's the change, but the EK initial is going to be 0 because it had a 0 initial velocity. Okay, let's keep going. Let's rearrange this and solve for the work done by the force of friction. We can rearrange that. We can add that to both sides and then take it away. So really we're saying that the work done by friction is going to be 110 times 10 to the 3 joules minus the kinetic energy final. And so the work done by the force of friction is 110 times 10 to the 3 joules minus 1/2 mv final squared. Okay, let's put these numbers in. And there's our final numbers. That's the 1/2 mv squared of the final. And so you end up with 1.83. That's the 3 significant figures. That's the work done by friction.